Hello. In this video, we are going to derive expressions for the energy and wave function corrections to a system that undergoes a perturbation. To do this, we are going to use the Schrödinger equation as shown on the screen, where h hat is the Hamiltonian and E is the energy. The energy is an eigenvalue of the eigenfunction psi. First, we expand the energy as a power series in the perturbation parameter lambda. Notice that when lambda is equal to 0, effectively we have no perturbation. E to the superscript 0, notice that this is not an exponent. This is the unperturbed energy. E1 is the first correction to the energy. E2 is the second order correction to the energy. Notice for the Hamiltonian, H0 is the unperturbed Hamiltonian. The blue H1 is the perturbed Hamiltonian. Similarly, for the wave function, the red psi0 is the unperturbed wave function. Psi1 is the first order correction to the wave function, and the green psi2 is the second order correction. We substitute the power series expressions for the Hamiltonian, the energy, and the wave function psi into the standard Schrödinger equation, which is shown in the first line in black. We first deal with the left-hand side of the Schrödinger equation, showing the series expansions that we substituted into it, and then we simply FOIL to get a total of 6 terms on the left-hand side. In the next step, we take each term and combine powers of lambda. Next, we collect all the terms with equivalent powers of lambda, and then in the bottom, we factor out the lambda. Now we do the same procedure for the right-hand side of the Schrödinger equation. First are shown the series expansions for the energy and the wave function, and then using the FOIL process, we get a total of 9 terms. In this step, we collect terms that have the equivalent powers of lambda. Once we have collected like terms in terms of the powers of lambda, we can factor out lambda from those terms. For the power series versions of the Schrödinger equation to be true, the coefficients of like powers of lambda have to be true. So if we collect the 0th power of lambda, we get the first line. If we collect the first power of lambda terms, we get the second line. And if we collect the second power of lambda, we get the third line. When we collect the 0th power of lambda terms, we get the first line, which simply says that the unperturbed Hamiltonian acting on the unperturbed wave function gives us the unperturbed energy times the unperturbed wave function. Essentially, since the perturbation has been turned on, nothing different happens in the first line. If we collect the coefficients of the first power of the perturbation lambda, we get the second line shown in the box, which includes the perturbed and unperturbed Hamiltonians H0 and H1, the unperturbed energy E0 and the first order correction to it, E1, the unperturbed wave function psi 0, and the first order correction to it, psi 1. If we collect the coefficients of the second order of lambda squared, we get the third line, the equation shown in the box. This series of corrections to second order will not be further discussed in this video. What will be expanded upon in a future video. We will attempt now to find out the first order correction to the wave function psi 1 and the first order correction to the energy E1. So let us write the first order correction to the wave function psi 1 as a linear combination of the eigenfunctions of the unperturbed Hamiltonian. We can do this because those eigenfunctions form a complete set, which means we can write any generic function in terms of those. So in terms of this, psi 0 is the ground state unperturbed wave function. Psi 0 sub 0 is the lowest energy eigenfunction. So we can write that as the ket 0. If we have the nth eigenfunction, we can write that as the ket n. And then the complex conjugate of the nth eigenfunction of the ground state unperturbed wave function, we write as the bra-n. In this step, we simply replace all references to psi 1 by this sigma c sub n times the ket n, which is just a linear combination of the eigenfunctions of the unperturbed Hamiltonian with coefficients c sub n. Once we've made that replacement, now we're going to left multiply by the bra 0. So this is the complex conjugate of psi 0 sub 0, and we integrate over all space. So we see this in the second line, and we've written in bracket notation. In this step, we write the entire equation in full bracket notation, and we focus our attention on the first term, the term that is in the black box. And we notice that since we have a sum inside the operator, we can pull the sum outside of the integral. And that's what we're doing in this particular step. Here, all we're doing is showing that the term in the box can be written in terms of an integral, which may be easier to visualize than the bracket notation. So therefore, for the rest of the derivation, we'll try to write everything in both bracket notation and in traditional integral notation, just to make it more obvious what is happening in the derivation. Here, as we proceed to the second line again, we notice that we pull the summation sign out in front. We also notice that for this particular integral, because the eigenfunctions of the Hamiltonian are orthogonal to each other if they have different eigenvalues, 0 and n will give an integral of 0 unless n is equal to 0. And then the value of that integral is simply going to be the energy E0, the eigenvalue for the eigenfunction psi 0 sub 0. We proceed to the second term, which we are essentially carrying through with no change because this is the integral of the ground state eigenfunction psi sub 0 with the perturbed Hamiltonian, whose eigenvalues we don't specifically know. So this is a term to be determined later. Next, we proceed to the third term, and again, we are able to pull the summation sign out in front of an integral. So here we pull the energy E0, being a number in front of the integral sign, along with the summation sign, and we're left with the integral of psi sub 0 star psi sub n. And again, these are going to be orthogonal unless n is equal to 0, in which case, because it's normalized, the integral there is going to be 1. So we simply get c sub 0 times e sub 0 for this expression. And here we see that third term again as we proceed through the derivation, and then showing its final value that we determined it to be c sub 0 e0 in the third equation. The fourth term is 0 e1 0. You can always pull a constant through the integral, and we get the expression we see in the second black box. Here is the same part of the derivation, but now showing things written as full integrals. We pull e1 through the integral sign, and we notice we're left with psi sub 0 star psi sub 0. Since it's an orthonormal basis, this integral is equal to 1, and we're simply left with the E1, the first order correction to the energy under the perturbation. Here we have in summary form what happens when we left multiply by psi 0 star, take the integrals. We end up with the third expression here, which gives us values for E0 and E1. We notice that we have a C0, E0 on each side, so we can cancel. And we're left with an expression for E1, the first order correction to the energy under the perturbation. And we notice we can get that by just evaluating the integral of the perturbed Hamiltonian acting on the ground state wave function, the lowest energy eigenfunction. Now to evaluate the first order correction to the wave function, we take the expression in the first line that we had from before, and whereas before we left multiplied by psi sub 0 star, now we're going to left multiply by psi sub k star, where k is not equal to 0, and then take the integral over all space. In the first line, we have a summary of this result if we write it in bracket notation. And in the second line, we take the liberty of doing some simplifications by pulling constants and or summation signs through the integral. So let us examine in more detail the first term, which is shown in the black box. And we see that we can pull the summation sign out in front of the integral. Here we see the result after we pull the summation sign out in front, and we realize, and we can write this result in terms of a particular integral. And we recognize that because k and n are orthogonal, the only time this integral doesn't disappear is when n is equal to k. So we get the result c sub k e sub k, this integral. For the second term, we have an integral of k with the perturbed Hamiltonian and psi sub 0. An important thing to keep in mind here is that we don't know the eigenfunctions of the perturbed Hamiltonian, so therefore there are no immediate simplifications we can make to this expression. And here is that expression written out literally as an integral. The third term, shown in the black boxes, has in the center we have a summation sign, and also we have a constant e0, and using the properties of integrals we can pull them in front and get a constant and then a summation multiplied by a particular integral. Here we see what those integrals look like written out explicitly, and then we recognize in the second line that we have the integral of psi sub k times psi sub n, and that is going to be 0 because those are orthogonal to each other, unless n is equal to k, so that is multiplied by the constant, gives us e0 times c sub k. For the fourth expression, we have this particular integral shown in the box, k e1, 0. We can pull the e1 in front, and then we have the integral of k with 0. Now, because of orthogonality, this is going to be 0 unless k is equal to 0. But our initial assumption is, in this case, that k is not equal to 0. So therefore, this expression disappears, is equal to 0. So now we're down to 3 terms because 1 was equal to 0. And we can subtract c sub k, e sub k from each side to get the expression in line 2, and then we can simply factor out the coefficient of c sub k. Now all we have to do is divide each side by this expression e sub 0 minus e sub k, and we have expressions for the coefficients c sub k. So to recap, what we were trying to do is we were trying to come up with a first order correction for the wave function psi 1 and do it in terms of the known eigenfunctions of psi 0 with some particular coefficients. So how do we pick the coefficients? Well, we use this particular expression to get the various c sub k's, to multiply the psi 0 sub k's. And if we can evaluate this particular integral and then divide it by e sub 0 minus e sub k, we would have the coefficients. A key part of this is that the eigenvalues of the Hamiltonian, at least in the ground state, have to be non-degenerate. So this e sub 0 minus e sub k cannot be equal to 0. I thank you very much for your kind attention. Please stay safe. And as always, have a good one.